because you're sitting like quite down the ladder in terms of like these effective theories, if you can get slight incremental improvements, you really can improve a whole hierarchy of other models that lie above you. So if you get slight improvements on DFT accuracy, you can improve your MLIP models and then improve any models that come from this.
Hi everyone, welcome to Let's Talk Research, the official InstaDeep podcast, where we dive into cutting-edge AI research and the stories behind it. My name is Bora Gulola, I'm a research scientist here at InstaDeep.
And I'm Massimo Bortone, I'm also a research scientist at InstaDeep. And today we will be diving into quantum mechanics, in particular some ongoing research at our company that is trying to apply machine learning to something called density functional theory. We will refer to this topic, broadly speaking, as ML-DFT for short. And to talk about this here with us, we have Jules Tilley. You might remember him from the MLIP episode from last month. And Zach Weller-Davies, who is the lead author on a forthcoming paper.
Thanks for having us, guys.
Thanks for having me back.
Brilliant. Hi, both. So I guess I'll just start with a slightly antagonistic question. So why do we care about quantum mechanics when we're modeling molecular systems, Zach?
Right. Yes. So I think, well, first of all, I think quantum mechanics is, it is the theory that we have of the way that things work, the physical world works as far as we understand. And so everything can be derived in principle from these quantum mechanical equations. So when you're studying, in industry, you might be interested in figuring out whether a catalyst, actually reduces the energy barrier of some system, or you might be interested in designing and figuring out properties of small drug-like molecules. And in principle, we can derive all of the properties that we need from quantum mechanics and from, in particular, the many-body Schrödinger equation. And so, for example, in school, you might have learned, whether or not, some reactions are endothermic, they absorb heat, some reactions are exothermic, they release heat. And these are the types of things that, in principle, we can figure out from the quantum mechanical equations that govern the systems. And it turns out, I think for many, many years before quantum mechanics, people tried to do this using classical mechanics and like Newton type laws. And unfortunately, that would have been much simpler, but it's not the way that the physics turned out to be. And so, we're stuck trying to solve these very complex, difficult quantum mechanical equations in order to predict the interesting properties that we care about for systems that are relevant to industry applications.
What makes quantum mechanics difficult, would you say?
What makes it difficult? It's compositionally speaking, it's a gigantic problem in the sense that particles interact with each other in ways that are way more complex than what you and I are used to in our classical world. They have this property called entanglement, which can only be described with, as best as we know, with very complex mathematics. And we usually say that it scales exponentially, which means that each time you add a new particle to the system, the complexity doubles, let's say.
Yeah, and by here we mean the number of states that the system can be in scales exponentially.
The number of
particles.
And so because of that, if you want to resolve something like the Schrödinger equation exactly, you will need all of the compute in the world and more. And obviously, eventually you will run out. So that is why exact treatment of quantum mechanics is not possible.
And so that's where density functional theory comes in, right?
Yes. In a way, density functional theory is a clever rewrite of quantum mechanics. So that's an approximate way to put it, but it's an intuitive way to understand it. It's a rewrite of the Schrödinger equation where you take all the complexity of quantum mechanics and you put all of it into a functional. And essentially, the functional takes as input what we call the electron density, which is the probability of an electron being in a specific, the probability of an electron being here or not in a specific point in space, and links it to the energy of a system. And that functional is extremely complex, right? It's we know it exists. There are proof that says there is such thing as a universal functional, but we don't know what it is, and we probably will never know. Where it becomes interesting is that with DFT, we can introduce approximation to that functional. And so we're trading off some accuracy, but we then gain a theory that allows us to look at the quantum mechanical problem in a way that scales a lot better. And so this is why density functional theory has been used for many years as the gold standard of chemistry, simply because it offers a very good trade-off between the accuracy of quantum mechanics and the accuracy that you would get from wave function methods, so full treatment of quantum mechanical properties, and the speed that you get from these approximations that you introduce and so on.
Yeah, probably important to mention here that DFT scales cubically, whereas most other wave function-based methods scale with higher powers of n.
Exactly.
Yeah.
And power 7, power 9, and
Exactly.
and also full treatment is exponential. And this is also where machine learning becomes relevant. In a way, we've been developing functionals for a very long time now, but these have mostly been based on experience and spending years in trying and testing different ways of building these approximations. Machine learning offers an opportunity to bring in data into the mix and bring in automated learning into the mix. So from data, we can learn a functional that should sort these approximations for us. So that's where the promises are in this field.
Yeah, and I think this is actually a more general thing in physics. So I think machine learning for density functional theory is an example whereby you are trying to sort of compress and encode the information of the full Schrodinger equation into something much smaller. But I think this is something that people have been doing for a long time. So for example, with thermodynamics, when you have your thermodynamic equations, you don't need to understand the full details of the particles moving inside the box. And I think DFT is one example of this, whereby instead of dealing with the full Schrodinger equation, you can deal with something more coarse-grained, the one-body electron density, but still get accurate predictions for the observables that you care about. So typically the energy of the molecular system.
Machine learning comes in as a very intuitive next step, in the sense of we have all this data, we have all this knowledge. So how can we use this data to create a functional that gets to the accuracy that we want to achieve?
Actually, yes, we have data, but compared to MLIPS, for example, we don't have as much data, because obviously as we go deeper into the theories, the methods become more expensive. Therefore, the availability of large-scale data sets becomes more difficult. So could you maybe explain, compared to MLIPS, how much data do we actually have?
Yeah, I think, we have a lot less data. I think recently, the big companies, Microsoft in particular, have been releasing beginning to release larger scale data sets for DFT, still within a smaller range of chemical space than the MLIPS. So I think DFT is still definitely within the early stages, whereby we have to have stronger inductive biases, for example, because we're in the sort of low data regime. But I think this is something, that will definitely change over time. So for now, because we're in the low data regime, we'll have to stick to models that are closer to the theory that people have been studying. And actually, this is something that's already been done for many, many years. A lot of the very successful DFT functionals are actually sort of semi-empirical. So they'll stick to a sort of ansatz motivated by theory, and then fit a handful of parameters to very small data sets. And I think in that sense, what we're doing is sort of going to the next step, which is, okay, we can now use slightly more data and modern techniques from machine learning to improve on the already existing semi-empirical functionals. But I think in comparison to MLIP really has, it still has a lot of inductive biases in terms of like locality, but you really are able to get rid of most of the inductive biases in the network and really get the network to learn. And I think this is where we hope that learning DFT functionals will go eventually. But for now, because they're so expensive to compute you have to use these very expensive wave function methods to compute the data sets. We're definitely in the early, it's definitely in the early stages.
So we mentioned that data is scarce in this setting, right? And that often in ML comes with certain limitations in terms of architecture and regularization and whatnot. What are you finding is the challenge here for you? And are you limited by the data scarcity in any way?
Yeah, so I think the data scarcity definitely plays a role in the sort of architectures that we can train successfully with. So typically we're not training with large scale transformers where you have very little inductive bias, and you let the model sort of learn everything from the data. Because we're in the low data regime, we instead deal with much simpler style neural networks. So for example, we'll use MLP layers very often. And really this comes down to the inductive biases that are inherent to DFT. So one big inductive bias is locality. So the DFT typically will use as input this electron density, and you can kind of visualize it as a point cloud. So you've got a point cloud, we'll discretize the electron density, and this then gets fed into your neural network model to predict a DFT energy. But we know the DFT functional is non-local. So for example, that the parts of the electrons in one part should talk in some sense to parts of the electrons in the other part. And there's a question of whether or not you should build this non-locality into your neural network, or if you should pre-process your features, for example, and then process this through a simple neural network. So typically what's been done in the past, when you're working in the low data regime, is to pre-process a bunch of non-local features and then put this through a simple neural network architecture like a multi-layer perceptron, whereby you have weight sharing across the points on the grid. And this is a very much simpler architecture. I think as the data grows, and for example, the new Microsoft paper where they introduced Scala, they generated a much larger data set that has previously been used. And this enabled them to actually incorporate some non-local effects into the neural network architecture. So they instead of pre-processing non-local features and passing them through a multi-layer perceptron, they didn't do any non-local pre-processing of features, but instead passed it through a neural network with a non-local architecture to then predict an energy. And I think you imagine that as you increase the data and you include more and more data in your training, that you can ultimately reduce the inductive biases that your neural network has, and eventually train something much more general that really can learn from the data and try and learn new physics that way.
Right. So this is still very much in the research phase of things as compared to MLDFT, which are already moving into kind of the development space. But so maybe from that perspective, actually, like what is the end goal for ML-DFT? Where do we think it's gonna shine, or what are we gonna use it for?
I think first, in terms of the history of the field, there's been a lot of attempts to make functionals, machine learned functionals for DFT. I think it's been slow in the progress, but there's been a few breakthroughs, in particular this DeepMind paper in 2021, led by James Kirkpatrick, the Microsoft paper that Zach mentioned. These are breakthroughs in the field that shows that basically provides a signal that there is something that can be done with machine learning for density functional theory. But the field still need to crack on quite a few walls to be able to apply at an industrial setting, or even just in a research setting. And I think that the main challenge for the field at the moment is really sorting out this balance between the inductive bias of the system and the availability of the data. As that progresses, I think there's two approaches that people can take when it comes to this type of models. You can decide to design them to be as specialized as possible, or you can decide to design them to be as general as possible. And what we're seeing is that at the moment, the specialization is quite beneficial because we are in a low data regime. We can create these systems or these machine learning models that are very targeted to a specific chemical property, specific types of molecular systems, and that perform very well for these specific tasks. And by very well, what we mean is, we talked about how DFT is an approximation. Ultimately, what we want to achieve is to get one step beyond this approximation, so to get to the next level of accuracy. And so this is what we are trying to get to. So we take data, which is very expensive to compute, which is computed at a quantum chemical level, which is more accurate than DFT.
And usually with wave function methods.
With wave function methods, exactly. And we're trying to get DFT to actually learn that data.
Yes.
And so, yes, for now, what we're seeing is targeted system, targeted properties is where the game is at for DFT. Later down the line, we'll have to think about, when this is cracked, we'll have to think about more general approaches.
Right.
And Jules, going back to kind of this idea that you mentioned in the last episode, right, of the trade-off between accuracy and speed, right, and how when you apply ML, for example, in MLIPs, right, you get essentially more accuracy for hopefully a gain in speed, essentially, as well. How does that does a similar thing emerge in ML-DFT as well? And kind of what is the regime there?
In a way, in ML-DFT, we are constrained by the theory of density functional theory. And there is very specific scaling properties that go with it. And so because we want to stay very close to the theory, it is very hard to make it faster. Actually, the way to make DFT faster is machine learning into atomic potential. What we can do is make it more accurate. And by taking this approximation and basically refining them on higher level theory data. So that's very much the approach here. In terms of the cost accuracy trade-off, in this one, it's very clear. It's the cost stays constant. We have no ambition making it faster, except maybe through very good engineering. But that would apply to any application of density functional theory. But really the objective is to go beyond in terms of accuracy, and I would say not necessarily quantitative accuracy, but qualitatively representing the deep quantum chemical properties that are happening.
And then essentially it's up to, the idea is that it's up to the practitioner to choose, I have this much in resources, right? I really need accuracy, or I need kind of speed and scale and kind of a lot more, right? I want to go really in depth, and I use approach 1. Otherwise, I use approach 2. Is that right?
Yeah, it's in generally what we see in practice. Yeah. At the industrial level, people will use filtering method, where you will start with the fastest method you can for a specific property, filter candidates for a specific molecular application, get the best ones, use a more accurate method, and so on and so on. Usually they end at DFT. In academic circles, sometimes they go beyond, so wave function methods and so on.
So would you say that, so at the moment, the goal for ML-DFT is to basically squeeze out as much information from the data as possible through methods of machine learning?
Yes, I think so, yeah. And for me, actually, I think there's sort of 2 reasons or 2 things that really excite me about ML-DFT. I think the first is, so you can imagine trying to squeeze out everything you can from the data to get slight accuracy improvements on DFT functionals already. And you can imagine doing this in a regime where DFT works, but you just want slightly better accuracy. And I think this is already quite exciting because of the sort of massive pipelines that use DFT calculations. So, for example, these massive MLIP data sets that have tens or hundreds of millions of calculations are all computed using a semi-empirical DFT functional. And so actually, because you're sitting quite down the ladder in terms of these effective theories, if you can get slight incremental improvements, you really can improve a whole hierarchy of other models that lie above you. So if you get slight improvements on DFT accuracy, you can improve your MLIP models and then improve any models that come from this. I think also one thing that's very important is that DFT doesn't work for all systems. And I really think that the goal of ML-DFT is to sort of compress as much information from these wave function methods as possible. And the hard and exciting bit is to try and do this in regimes whereby we currently don't have a good compressed representation. So where DFT fails at the moment. And for me, I think this is super exciting because you're really trying to learn, it's kind of like learning new physics. So even though we know how to do the wave function methods, we don't know how to write this in terms of a sort of simpler theory with where the electron density is the main object of interest. And yeah, I think doing this is very difficult, but very exciting, the exciting part of DFT. So I think for me, there's two main regions: incremental accuracy improvements that get propagated through the pipeline, but also trying to discover new physics that then using tools like MLIPs, you can actually sort of study at scales that you previously would never have been able to look at them.
Yeah, and on that first point, right, that kind of echoes what we've been seeing in a lot of different fields as well, right? So recent, for example, protein structure prediction methods have often relied on kind of a previous generation model, for example, just creating a little bit more accurate data that you can then feed in, and hopefully that improves. You're taking that basically a step further and saying by just improving the information that kind of sits at the base of it, we can essentially have that propagate through the system.
Yes, yeah. And actually, I think this is one of the very cool things about doing ML for physics, is because we actually have the sort of source of truth. And so in principle, it should be like a sort of perpetually improving hierarchy as you use more and more compute, if you're clever enough to get the right inductive biases as you climb the ladder. So yeah, as you said, like, well, in principle, we have the Schrodinger equation. We can generate, if we had infinite compute, as many systems with huge data sets to then try and train an ML-DFT functional, which would be more compressed, quicker to run, and try and build the ladder. And so I think this is a third thing maybe that's very exciting, is that like actually we do have access to, because we're generating the data synthetically, that we can keep generating more and more data and then improving the models over time, using the models that the improved models to then improve more and more models. But this is definitely early stages. This is the dream for the future, I think.
Yeah. And the bottleneck is still getting the data.
Yes, of course.
Wave function methods scale terribly yet.
Yeah, you need approximately infinite compute to to go up.
But I think it's like we've talked about, and when we were talking about MLIP, I think there's clearly an effort by a lot of players in the community to actually produce that data, use a lot of idle compute to actually leverage the capabilities we have to generate relevant data for this specific application.
Yes, I think this has definitely formalized in the MLIP community. I think it would be nice to see some efforts at the DFT level. In the future, I'm looking at like neural networks for quantum states or NQSs. If those could come forward and actually be a source of sort of synthetic data for training DFT functionals, that be, I think, a really interesting research. But we'll have to see. And
I think there are definitely many groups and startups that are trying to develop these wave function methods to compute relevant information that can be then used for training set for either machine learning density functional theory or MLIP. I can name, for example, Simulacra AI, which we've had conversation with, and so on. But I think that the generating data for ML-DFT as additional complexity. It's not only a problem of compute, it's also a problem of choice and design and validation. In a lot of cases, wave function methods work and they can also fail, and sometimes in unpredictable ways. And so that creates a layer of challenges that makes it quite difficult for sort of a joint effort, a joint community effort to generate all that data and the validation that come behind it.
Yeah. How do you go about actually testing and benchmarking ML-DFT methods? Because DFT is actually not a variational method. So if you get a lower energy, it doesn't necessarily mean that you're closer to the truth. Whereas in other methods, most wave function methods are variational. So actually a lower energy is a better energy. How are you thinking about this?
Yeah, I think this is one of the big challenges, I think, within DFT. And I think actually, maybe backtracking slightly on what I said before, I think this is one of the challenges within when generating data in general with quantum chemistry, is you can pick a method, but you can't necessarily be sure, because typically you'll make some, you can't necessarily be sure that when you've minimized, say you pick an ansatz for the wave function and you try and minimize the expectation value of the energy, you can never be sure that actually the energy you've reached at the end is the true ground state energy. And you can only, I think this is one of the very difficult parts of quantum chemistry. Typically within DFT, I think you can imagine doing two things when benchmarking your functional. You could, if you want to just purely test the machine learning part, I think sort of a valid way of testing whether or not your theory is working is to generate synthetic data at some level of theory and then benchmarking against this. But obviously this doesn't necessarily work because the level of theory that you generate your data at might be incorrect. So if you use couple cluster theory to generate a data set and validate on this, it might actually be that you learn the wrong energies to the true energy. I think so. In practice, what we do is people have generated data sets at some level of theory that's very high, and they have a lot of expertise when they generate these data sets. So they have the correct inductive biases in their wave function methods.
Yeah, and I guess often they compare to actual experimental values, and they know, okay, we're 90% likely to be within like chemical accuracy of experimental data.
Yeah, exactly. So we benchmark against these types of data sets. But yeah, I think one of the problems is generating large scale data sets is really difficult to make sure when you do this that actually your energies are correct, even if you're doing a very expensive wave function method.
And I think ultimately, and for now we're doing all of these tests, but ultimately the real test is it useful in a practical setting?
Yes.
And that comes with, you can pass all these tests and then try it on some new method that someone want to develop, a new system that someone want to create, and you will not know if it works or not. So I think that the ultimate test is knowing that someone can use it almost blind, and be able to describe qualitatively what's happening from a fundamental perspective and say, well, this is accurate and this is actually useful for the application.
Right. Yeah, I guess that's like in the case of MLIPS. Also, the ultimate test is do users find it useful, and does it satisfy their requests on like test systems and things like that.
And we touched on the idea that kind of certain bits of chemical space are easier to generate data for, right? Is that because there's been a bias historically towards exploring certain bits of chemical space more, right? I'm thinking kind of, I suppose, small molecule like drug-like molecules will be very well studied, I imagine, versus other kind of types of organic molecules, say, that don't have those same properties. Is that a correct assessment?
I think there's definitely some of that, but I think it's also a lot of quantum chemistry is not as complex for everything, and approximations that you can make to quantum chemistry to get accurate results are also sometimes very obvious in some systems, and some other systems they're not.
Yeah, I think this is it's a very I think really is ingrained in the physics of small systems. So I think, for example, density functional theory is typically built, or the functionals the original functional was based on what's called this local density approximation. And essentially what this means is you'll compute accurate energies when your electron density is very slowly varying or almost constant. So originally there was this local density approximation, then people came and improved it using these gradient approximations, whereby your density functional depends not only on the value of the electron density, but also the gradient. And this works slightly better when you had these slowly varying electron density. So for example, in metals. And so this was coming from in this top-down approach where you're actually motivating them theoretically. But it turns out these don't work so well for molecules for various reasons. They just don't capture the physics correctly. And so people have then since come and improved the functionals. But typically you need to do this using theory. You have to have very good knowledge of the physics of the systems. And I think this is the same for generating the data using the wave function methods. So for example, Massimo's the expert on these wave function methods, but CCSD works very well for like weakly correlated systems. And if you go to a system where the electrons are strongly correlated, you'll typically get very bad results. And so you get certain areas of chemical space where it just happens to be the case that the physics of the physics of the chemistry matches with the inductive biases that we're are very well studied in these wave function methods. And outside of this, it becomes a very big challenge to actually get the physics right to then describe so I think it's more of just we know how to deal with certain regimes, and other regimes remain difficult and challenging.
So it's much more about the complexity of the system and the complexity of its behavior than it is about kind of what exactly the type of species is, right?
Yeah. So for example, I think, one example of this would be like dispersion energy is very hard to capture in DFT because it's a lot longer range, whereas DFT more accurately captures like the covalent bond energies in systems. And this is just a byproduct of the physics itself. So rather than, the actual sort of makeup of.
And there's also a whole realm of chemistry for which density functional theory actually is known not to work, in the sense that the theory is not valid for these systems. The guarantees that you have in DFT might not work in systems that are quite degenerate, for example. We don't know it to work for excited states and so on in a particularly reliable way. So I think that while DFT is a very important endeavor, while machine learning DFT is a very important endeavor, it's not necessarily a silver bullet, in the sense that there are many other things that will need to be explored.
Yeah. I mean, this kind of reminds me a lot about certain problems that we have in the kind of AI for biology domain, where you actually, even if you have a perfect system, right, rather perfect ML tool, let's say, you still need a lot of domain expertise to be able to interact with it accurately and to make sure that you're actually doing things that are sensible.
Yeah, I think this is especially true because, you have, even at the low level, because you don't have this source of truth. So you have to be very careful what you benchmark against, because you can probably do some very wrong things if you haven't got the physics right. But I think as well, what's cool is you can also go sort of up the ladder and test these things experimentally. I guess you can only test certain things, but for example, like equilibrium structures you can predict using DFT, and then you can also test not just from the lower level theory, but you can also go up and test certain properties from DFT, and then with experiment, and see if your predictions work where maybe some previous DFT experiment failed, or if you predict a new material because your functional now predicts some physics that you didn't previously expect. Like, does it exist, and can you actually observe these properties experimentally?
Yeah, I guess in this space, it's definitely true that there's not one tool for everything. There's many tools, and they all have their strengths and weaknesses. And usually what works best is trying a bunch of methods and compare results. And that's where you get most of the information out of your systems usually. That's definitely true for DFT because you have so many functionals to test and play with. But it's also true for like other theories and methods.
Yeah, I think actually that's a good point. At the moment, there's sort of another thing that's potentially exciting about DFT, but maybe is sort of a pipe dream, is that at the moment people use many different functionals depending on the system that they care about. So if you're interested in metals, you might use the PBE functional, which is this DFT functional that depends only on the electron density and gradient, because you have a very slowly varying electron density. Whereas if you're interested in small drug-like molecules, you might use a different functional like B3lib, which includes some proportion of exact exchange. And I think one of the hopes of DFT is that you can compress all of this into one functional so that you don't have to worry about the different domains where you apply it. But
you mean ML-DFT?
Yes, ML-DFT. But yeah, I think this is one of the hopes, but then I think one of also the challenges, and maybe why you might want to actually end up focusing on specific systems, because learning a general DFT functional might be too challenging.
You're gonna need lots more data for that, obviously, but also you're gonna have to have essentially the theory necessary to generate that data, right?
Yes, and I think one of the challenges is that typically where DFT fails is also where the wave function methods often are more challenging. So for strongly correlated systems or transition metals, actually not only does DFT not do particularly well, but also we don't really have an efficient way of generating the data. So yeah, really we need to also be working with the wave function people to sort of build up the whole pipeline of these machine learned theories.
Yeah. And that's a very common thing across the entire ML domain, right? Garbage in, garbage out is always, if it's not accurate data going in, then.
Yeah, but at the same time, you also need to keep in mind that these functions are going to be used in a specific setting, and maybe in some settings you don't really care about being very general on certain systems. So as we said, you might just want to specialize and actually get specialized data for the systems you care about. And that's also the hope of using ML here, to build like ad hoc functionals that are specialized for particular problems.
Yeah, I think it's interesting because it's an interesting physics question, is like actually if you study a metal or a transition metal or a drug-like molecule, like is the physics actually that transferable in this sense, or are you actually better off just ignoring everything you learn because the electron density just looks so different that it doesn't transfer. And I think this is one of the cool and interesting.
Yeah. And on the note of training, actually, would you be able to say sort of in a few steps, how do you actually go about training a ML functional?
Yes. So I guess there's maybe we can start by maybe briefly overviewing how these DFT functionals are used in practice to in the DFT sort of system to compute the energies and properties you care about. So what a DFT functional does is it gets this electron density and predicts an energy of the system. But what you care about actually is the minimum energy. So you want to find the electron density that minimizes the energy. So this is really a search space over possible electron densities. So if you imagine you have your DFT functional, you're happy with the functional that you've picked. You really want to search over all the possible electron densities that minimize the energy. And this is a very, in practice, this is a very big search space. But you can discretize it on a computer and go through this, what's called a self-consistent procedure to try and find the electron density that minimizes the DFT energy.
And we should maybe say here that there's already an important approximation here because we're working with Korn-Sham DFT, which is already has certain assumptions about the density or how we represent the density, which make this whole thing feasible.
Yes, that's an important point. But yeah, so in general, you go through this self-consistent procedure and your goal is to find the electron density that minimizes the energy of your DFT functional plus the DFT functional is defined as like a remainder term, but you can just picture it as just some energy functional that we'll call the DFT functional. You want to find the minimum energy. And so there are sort of two things that you can, sort of two ways I think you can imagine training a DFT functional. One is you sort of start off with your molecular graph. You have an initial guess for your density, and you go through this entire SCF procedure using an auto-differentiable paradigm, and you'll predict an energy and a density if you need to, and then you can back propagate through the entire SCF procedure to get the gradients to update the parameters of your neural network. So if you do it like this is sort of the ideal way of doing it, because you really get all of the nonlinear information that you get through your SCF cycle. But this is very expensive, and so this is one of the things we do. But typically, we'll only do this for small molecules. So we view this as the best way of training small molecular systems when we have the computational capacity to actually train through this SCF cycle and get the gradients back. The other way you can do this is essentially just you don't go through the entire SCF procedure, but you start off with what you think is a very, very good initial guess for the density. So you can get this, for example, by using another DFT functional to predict a density. And typically what you find is that, for certain systems, you'll find that actually the error in choosing a different, so if you have the same density functional, but you evaluate it on two different electron densities. So long as the electron densities are, reasonable guesses, actually the error in energy is pretty small typically. So this is true for certain systems. Other systems, for example, barrier heights often have, this is not true. So actually if you pick two different densities, you'll get a wider range, you'll get a big energy variation. But in the systems without this density driven error, what you can do is you can just take an initial guess and then do one forward pass of your neural network. So this enables you to train much bigger systems. And so what we actually do is we do a hybrid approach whereby for smaller molecules, we'll train through the entire SCF cycle and regress against energies using the entire cycle. And for bigger molecules, we'll just do one forward pass using an initial guess generated by what we think is a good DFT functional. And we make sure that, when we do the sort of one-shot regression, that we don't include the systems that have too much density-driven error, because otherwise you can't be sure that your energy, your output will be correct when you go through the SCF cycle in practice.
And that might sound like an enormous amount of compute, but it's very much required in the context of DFT. In all of machine learning, we have this problem of overfitting, and basically you have a set of data you're trying to learn on, and you're trying to extrapolate what happens between the points. And for DFT, this challenge is extremely high because of the complexity of the space that we're trying to learn. So this SCF loop is, in a way, this training through the SCF loop is a form of data augmentation. You can think of it as a form of data augmentation, where we allow the model to learn through tons of different configuration of the electronic densities, so that it regularizes itself. It learns to extrapolate what happens between the points. And it is, it's been a recurrent problem in the ML-DFT literature, and we can quote again the approach of the paper in the DeepMind paper from 2021, where they used a separate loss, which has specific components of the SCF cycle in there to actually regularize the potential that we are trying to learn.
Yeah, I think one way of visualizing this is that, so the DFT procedure, you care about minimizing, you care about the energy that you get when you search over all electron densities. So you care about the minimum over the space of electron densities, the minimum point, the energy of the minimum point. But in practice, when you do Cohen-Sham DFT, you have to have a method that gets you to the minimum point. So you can't just do a crazy search. You have to pick a specific search method, and typically this will involve learning the gradients as well. So you have to have good gradients of your neural network or of your DFT functional with respect to the input, so the electron density, so that you have a method also of getting to the minimum. And this is exactly what we hope, or what the SCF cycle, what the SCF Go training through the SCF cycle does, because you start with an initial guess, and not only do you have to get the right energy, but you also have to have a method that gets you to the right energy. And I think going through the SCF cycle is a sort of more accurate way of doing this versus the using this approximate SCF loss, which essentially is at the minimum enforcing that the minimum is a minimum, but it doesn't ensure that actually if you started with a random initial guess that you will get to that minimum point.
Is that because you can get stuck in a local minimum?
Yeah, exactly. Yeah.
Okay.
This is particularly problematic, I think, with ML functionals. If you don't train through, say, the SCF cycle, you're at risk of not just getting stuck, but also like veering way off if your derivatives are not well defined. And I think this is actually a similar problem with the MLIPs, why you don't just train on energies, but you actually train on forces, because you care about actually being able to do MD simulations, and really you care about getting this whole surface near the equilibrium geometry right as well. And I think DFT is like exactly the same problem, but you just have, instead of searching over geometries, you're searching over the space of electron density. So it's a much bigger search space, but the analogy of like the MD is a little bit like, or like doing geometry optimization with an MLIP is a bit like doing this, finding the minimum energy of a DFT functional.
So obviously this is a massive problem, right? Really, really complex, as we've discussed. How have you personally found working on it? So
it's been a mixture of like exciting and very painful. So my background actually was gravitational physics. I did also a little bit of quantum during my PhD. So the initial phases of the project, I had to sort of really delve into the depths of the many-body Schrödinger equation, understanding DFT. And this was very exciting. I think, because of the technicalities of DFT, and in particular, the sort of scales at which you see DFT fail on your laptop are quite small. So when you're trying to train a DFT functional, you really have to, you have to go straight in. You have to be training on clusters. You have to make sure that you do things in a way that means you don't run out of memory. Your data sets are typically enormous in terms of size, because you have to store things like the electron density at each grid point, and you have to store this somewhere. So in that sense, I think it's been both very painful, but then also a very rewarding experience, because you have to deal with a lot of tools, and you have to learn a lot of things in order to be able to just get the setup to train a DFT functional. And I think there's a lot of very transferable skills that come from studying DFT. So for example, though I haven't worked on MLIPs, I think you get a good insight into the MLIPs, because ultimately the DFT data gets used to train MLIPs. And so in this sense, I think it's been very rewarding.
Yeah, I can only imagine, right? We probably have barely scratched the surface, and I've definitely learned a lot. So thank you so much, and hopefully we'll have you back at some point.
Yes, thanks guys for popping by and talking about quantum mechanics. It's definitely one of my favorite topics.
Thanks for having us.
Yeah, thank you very much.
And to our listeners, we want to wish you all a happy and healthy winter break. We will be back in 2026 with a special episode.
Thanks for tuning in, everyone. We'll see you next year.
Bye bye.